Hi everyone, welcome to Vedantu English. I'm Diksha Kaushal, your chemistry master teacher. So everybody, do let me know in the chat box if I'm clearly visible and audible to all of you or not. And today we will be doing valence bond theory from coordination compounds, right? In the last two lectures, we have completed two things. One is classification of ligands, general like what are coordination compounds. Then we discussed about your nomenclature, IUPAC naming of coordination compounds, right? Werner's theory also we discussed in the last class. And I gave you two questions, two homework questions for that. And let me just see that how many of you actually do your homework. For that, I'll have to visit Vedantu JEE. Now I'll just see how many of you have religiously done your homework and how many of you are like, doesn't matter, ma'am, because I see very non-seriousness from you side, from your side, guys. Not even a single student who has done the homework, right? Not even one single student who has done the homework. So that's very sad on your part, and I'm not so happy by seeing that, right? So that's very sad. My health is better now, right? I am better. My health is also better. So I am recovering and I'm very like positive about that thing, right? Okay. So very good evening, Ibu, Nikhil, Frida, RTG, and someone broken heart is there, right? And Sharon, yes. So yes, Sidesh, I am fine. I am better today. You can see this from the energy as well. Now it's better, right? I'm feeling much better. I just hope still I'm on antibiotics. I really hope without medications also I feel better, right? So let's wait for 1 week more, right? Okay. So firstly, let us see the homework. And guys, today also I'll give you homework. Do your homework, right? Be regular in that, right? I don't even have to say, like, if I have to push you to do homework, then you don't deserve that JEE seat. Trust me. If I have to again convince you one simple thing that is homework, then students, you are doing something very wrong in your life, right? If you're preparing for JEE and you are just taking things very non-seriously, then, you need to remind yourself you have just 5 months, right? And attempt one is what matters the most, right? So focus on that. So, and before going, one more very important thing that we are providing you scholarship based on MVSAT scholarship program, right? The registration, there is no fees for that. Totally free of cost. You can register yourself, you can give the test. And after that, based on your marks and your AIR, you will be competing with national, like all competition will be among all the students of this India, right? So when you are competing nationally, then in that case you will get to know that okay, what is your level, right? According to that, you'll be provided with the scholarship. And if someone is getting like really good ranks, for them we have worth 2 crore scholarship, right? 2 crore gifts, like you have iPhone, iPad, and all the other study materials as well. Vedantu courses will be 100% free for you. But for that, you need to enroll yourself to the MVSAT scholarship program. Here are all the things that we can provide you in the MVSAT scholarship program. And the dates for offline are 4th, 5th, 11th, and 12th of October, right? So you'll have time to prepare yourself. Very general questions will be asked in the MVSAT, right? Okay. Now let's see the homework that you have. Cobalt 3 chloride. They are saying that you have cobalt 3 chloride. Okay. CO3 positive you have. Forms several octahedral complexes with ammonia. With ammonia, there is ammonia also. There is chlorine also. They are saying which of the following will not give test for chloride ions in silver nitrate. If this particular compound, when it is reacted with AgNO3, there is no AgCl. precipitates that are formed, that means how many Cl will be outside the bracket. Students, this is inside the coordination entity. Number of Cl outside the bracket will give you the number of AgCl. Now we have no AgCl, that means no Cl is outside. But he is telling that some chloride ions are outside. So that means it can be CO, chloride ion will be there, right? Now you have these options. Let's see if you can make it or not. If I talk about this option here, if I'm keeping all the Cl3 inside, then I need to keep 3 ammonia, then 1 NH3 will be outside. That is not correct. NH3 acts as a ligand, not a counter ion, right? So that is not possible. Now, next thing is you have 3 Cl, you have 5 NH3. So Cl will always be inside only because there is no Cl outside, right? So all the 5 NH3 you have to keep inside, which is again not possible because then you will have 5, 6, 7, 8, 8 coordination number in cobalt 3 positive, which is not possible, right? So this is also ruled out. Third is you have 3 Cl and you have 6 NH3. Then you will have to put 6 NH3 inside. Coordination number will be 9 and they are telling you that it is octahedral complex. 6 is the coordination number here, right? So this is also not possible. Last possibility is you have 3 chlorides and 3 ammonia, right? And that is your final answer, right? If you see this, if I have 0 oxidation state, this will be X minus 3 is equals to 0. That is X is equals to plus 3 and cobalt is coming out to be in plus 3 oxidation state. So answer will be D is your correct answer. Okay. D is the correct answer. Okay. Yes, I am fine, I am better, right? That's why you can see energy in the class. Okay. So, next is what is the oxidation number of central metal ion in this particular compound? Was it like that of a difficult question that you didn't answer it in the comment section? Huh? I don't know why you guys don't do your homework. I really don't get it, right? It's like it's like spoon feeding, right? If I'll be teaching you everything, not giving you homework, and you feel that, okay, that is actually spoon feeding, which I don't want to do, right? So, this is nothing but how you will calculate X. NH3 is neutral, so it will be plus 0, plus 0. Br is negative, so it is minus 1 is equals to plus 1, so X will be equals to plus 2, so it will be nickel plus 2 is the correct ion here, right? Okay, understood? Yes. So tell me, students, is there any question in the previous lecture? Any doubt from the previous lecture? Any doubt? Any doubt from the previous lecture? So that we can start with this. Now we are actually left with some very important topics from coordination chemistry. First is this VBT, then you have CFT that I'll take in the next lecture, then isomerism and metal carbonyls, right? So that I'll take in the next lecture, right? So total in 5 lectures I am completing coordination chemistry. Now, today we'll be doing VBT, Valence Bond Theory, very simple, very easy, but there are some exceptions that are involved here, and for that you don't have to worry. Usually, theory students understand, but these exceptions are difficult to understand, right? So, I have kept all the exceptions in this particular table, in this particular points, right? You will see all the exceptions for VBT theory because the questions are asked from exceptions, right? So that's why we'll be taking care of the exceptions as well, right? Now, starting with the theory, can I see your energy in the chat box? Can I see your energy? How's the energy? How's the Josh, guys? such a low energetic class, right? Let's see why the students have not joined. Why? Sure. Okay. So now let's see that if you see valence bond theory, right? Guys, I will not teach if I don't see your energy in the chat box, right? That's not how you should behave, right? I want to say, yeah, wake up, yeah. Why are you sleeping in the class? Why are you sleeping in the class? Like, why are you making this topic so boring, ma'am? It's as if, it's like I'm teaching you at 2 a.m. in the morning, right? You're behaving like that. I know it's Sunday. You're like, ma'am, I wanted to enjoy my Sunday, right? But just 1 hour class I'm taking, like extra class I'm taking. Even I am ruining my Sunday for you, right? So, yes, very good, very good. So, let's start. And here we have valence bond theory, right? So, valence bond theory is based on the valence electron, right? We'll talk about how. First thing is you need to understand that this theory is going to give us what? According to this theory, metal ion under the influence of ligand can uses n minus 1d or ns or np or ns, np and nd orbitals for hybridization, right? To yield a set of equivalent orbitals giving different geometries. So, what we will do in this theory, a compound will be given to you, right? What is going to be the way of solving the questions, right? So a compound will be given to you, right? A compound will be given to you. Now in this compound, you have to find the oxidation state of metal. Firstly, you will find the oxidation state of metal, right? Okay. In that oxidation state, you will have two kind of things. See how it will work. You will have n minus 1 d orbital. You will have ns. You will have np. You will have nd orbital. Right? This will be the situation. Like you can have 3d, 4s, 4p, 4d. Right? These kind of situations you can have, right? So either it can be the inner orbital or it can be the outer orbital, right? Now, based on this, you will have certain hybridization. Now, next thing is you will check for the pairing or non-pairing. Whether there is pairing, I'll explain everything, okay, with the help of examples. And you will see no pairing. This will depend on the ligand. This oxidation state will depend upon the compound. You will calculate the oxidation state. Then you will write the electronic configuration, right? Then you will see whether there will be pairing or there will be no pairing. This is the most crucial step here, right? And after that, you will have the answer like, yes, after that you will have your answer according to pairing and non-pairing. Now, I will give you some examples of that, right? But you have to understand firstly each step here, okay? So, if a compound is given to you, you can easily calculate the oxidation state of metal that we have done before also. But ma'am, the question is, how will I get to know whether there will be pairing or there will be no pairing? Based on pairing and no pairing, you will have two things. That is, either you will have different type of hybridizations. You will have sp3, you will have sp, you will have dsp2, right? Then you will have sp3d2. You can have d2sp3. You can have dsp3, right? So these are the different kind of hybridizations which you can see, right? So based on these different hybridization, we will have certain geometries, right? So one by one, firstly, I will talk about each point here. So firstly, I am going to talk about this point, that is which hybridization is giving you what kind of geometry. Okay, so one by one we'll talk about everything, right? First thing is we know that metal, right? If I talk about this is the metal, there is a ligand. Okay, what exactly is happening here? So this ligand is electron donor and this is electron acceptor. So what will happen? Why they are becoming friends? Because ligand wants to donate the electron, right? And the metal ion wants to accept the electron. That is the main thing why they are making bonds, right? So ligand has some electrons. It wants to donate this electron to the metal. Now, ma'am, why we have transition metals only? We'll talk about only transition metals here. We'll talk about D block metals here. We will not talk about aluminium. We will not talk about magnesium. We will not talk about sodium. You will not see that it's like this is sodium and then you have CN3. No. You will see nickel, copper, cobalt, the transition metals, the D block metals. Why? What is the quality of D block metals? What is the quality? Right? The quality is that they have empty D orbitals. Guys, simple thing is some guest is coming to your house, right? Some guest is coming to your house, right? So they are thinking that, okay, we want a separate room. To give them a separate room, what we do, we have to vacate a room for them, right? Only then they can sleep in a separate room, right? So they will go to only that house which has a separate room for them. I know that what happens in middle class home, what we do is we are like, okay, have the mattresses on the floor and we all will sleep in one room, right? But yeah, we are talking about those kind of guests who are like, huh, we throw a lot of tantrums. We want a separate room, like AC, separate room for us, right? So these are those kind of these electrons that this ligand is donating. It is that guest who has a lot of tantrums. They want a vacant orbital, and D block elements, D block elements have vacant d orbitals, have vacant d orbitals where they can easily sleep and relax, right? So that's why it is preferring d block elements, right? So ligand is donating, and that's how you have a coordinate covalent bond here. Now, why it's a coordinate covalent bond? Why? Why it's a coordinate covalent bond? Why it's not a covalent bond? Because in a covalent bond, this is A and this is B. This A is having one electron, this B is having another electron. They will share this electron. Each of them has one electron. But in coordinate bond, this A has no electron, this has two electrons. It will share both the electrons with A. So that is the difference between this is covalent and this is coordinate covalent. Right? You can simply say coordinate bond. So that's why these are called as coordinate compounds, because coordinate bond is formed between them. Right? Okay. Now, next step is to understand the postulates. Right? Each postulate I'll teach you. First is sentimental atom has empty orbitals, because of which for accommodating electrons donating by ligands. Ligands are donating the electrons. They're like, I have one empty room for you. You can live here, right? Second is the formation of complexes involving reaction between Lewis base, that is your ligand. What is a Lewis phase? Why ligands are called Lewis phase? This is also a very important question, because ligands are electron donors. Okay, so this is a reaction between electron donors and electron acceptors. These are electron acceptors, and that's why they are forming coordinate bond. Coordinate bond between them, right? Third postulate is it is related to hybridization, right? So how we have hybridized orbitals, okay? Hybridized orbitals are allowed to overlap with ligand orbitals that can accommodate with this. Now I'll teach you this with the help of one example. What is hybridization? Hybridization is that, for example, you have, I'm taking one example here. For example, you have CO2 positive. Okay, CO2 positive. Cobalt is 27. Cobalt is what? Cobalt is nothing but it is argon 4s2 3d7. You take out 2 electrons from here, it will be 3d7. Now these are the vacant electrons. Now how do you fill it? You will fill it like this. This is D. This is then S. Right? This is then P. Right? This is another. Wait a minute. I'll just keep it here, 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 and one more orbital here. Right? Okay. So now D block has 5 orbitals, P has 3 orbitals, right? And the D again will have 5 orbitals. Okay. So now, as I told you, there will be n minus 1D, ns, np, nd. Okay. So like here you have 3D, this will be 4s, 4p, this can be 4d. Okay. So like this you can write it, right? Now, after this, what we are going to do, let's say how many electrons it has in 3D. It has 7 electrons, right? It has 7 electrons. Now see one thing, 7 electrons you want, it's a very big mistake that students do. 7 electrons means 1, 2, 3, 4, 5, 6, 7. 7 electrons it has, okay? 7 electrons it has. Now, ligand is approaching. Now, maybe there is, let's say there is Cn negative. Let's say the compound is having Cn negative ligand. Okay, I'm just assuming this, that the compound is having Cn negative ligand. I told you that here you will have a concept of pairing and no pairing, right? So that also I'll tell you which will cause pairing and which will cause no pairing. That itself is a very important point of this VBT theory. But for now, I'm telling you that Cn is a strong, it causes pairing, right? It will cause the pairing, right? If it causes the pairing, what will happen? We will have this here, right? Again, you will have this S, you will have this P, you will have this D, right? Then 1, 2, 3, 4, okay? 1, 2, 3, 4, then 1, 2, 1, 2, 3, 4, okay? Now it causes pairing means 1, 2, 3, 4, 5, 6, and this will be 7. Now, these are the empty orbital which will tell you the hybridization. So, hybridization is judged by the empty orbitals. Right? Hybridized orbitals are allowed to overlap with ligands. That means if I say, let's say, okay, I'll just put it as CO3 positive because only then that is possible, right? If this is CO3 positive, because that case will not be possible, right? And I'm saying that it's an octahedral compound. Let's say this is COCN6, right? 6 means 6 ligands you have, okay? So, and here if I found out x minus 6 is equals to minus 3, that will become plus 3 only. That is cobalt plus 3, right? So, firstly what I did, from the compound, I was finding out the oxidation number. Then I solved the value of electronic configuration. Now, hybridization will occur for the empty orbital, right? So, for how many empty orbitals it has? Earlier it had 1, 2, wait a minute, yes. This will also be 1, 2, 3, 4, 5, 6. Okay? Now it will cause the pairing. If it is a strong field ligand, it will cause the pairing, and you will have, you need 6 ligands. So 1, 2, you need 6 rooms. 1, 2, 3, 4, 5, 6. And that's how this hybridization will become D2sp3. Okay. But if I say I have a weak field ligand, right? If I say I have a weak field ligand, right? You have a weak field ligand here. Let's say you have chlorine. Okay. Let's imagine you have chlorine here. Okay. You have chlorine here. This is Cl, Cl6. Okay. You have chlorine here. Now, if you have chlorine here, coordination number is same. You find out oxidation number will be same. But now I am saying it is chlorine here. Chlorine does not cause pairing, right? So if it does not cause pairing, what will happen? What will happen? All of this, if you see, wait a minute. What will happen here? All of this will not get any pairing. And now the empty orbitals that you have is sp3, 4 rooms, 5, 6, 6 rooms. 6 rooms you need because you have 6 guests here. So 6 rooms you need, right? So now you have sp3d2. This is sp3d2. So the hybridization that we are talking about is based on the empty orbitals that you have, right? And that will be based on pairing or no pairing, right? I took example of only one metal ion. I gave it pairing ligand and this is a non-pairing ligand. One is causing the pairing, other is not causing the pairing, right? So how does hybridized orbital will look like? It will be like this, okay? It will be like this. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. And this whole will be D2sp3. And this will be your D3, whatever was there, right? And here you will have, I am mentioning it by these crosses. These crosses are nothing but ligand are giving the electrons. So one Cn is going to give you 2 electrons because one Cn means Cn negative. So it gives 2 electrons, right? So this is paired with one Cn, another Cn, third Cn, fourth Cn, fifth Cn, sixth Cn. That's why this is called hybridized orbital. This is the hybridized orbital that will be different for every single compound, right? So hybridized orbitals are allowed to overlap. They are overlapping because these electrons are given by the ligand. Overlap with ligand orbitals that can donate electron pair. I am showing you by this. In reality, what will be happening? In reality, you know what is happening in reality? Guys, can you visualize what is happening in reality? In reality, there is these d orbitals, right, that are overlapping with the hybridized orbitals. Overlapping with the hybridized orbitals, and here you have the 2 electrons. In reality, this thing is happening. Okay, that's why they are saying that overlap with the ligand orbitals, right? Okay, understood everyone? Hope so this point is clear to you, right? Okay, yes. Okay, yes. Piyush, because the name of the channel is English, right? That's why I'm teaching in English, right? Okay. So now, but I think my English is not that English. It's not an English accent that I am faking here. Like, hey, buddies or Shulta. It's not that difficult to understand my English. It's like a Hindi English only that I speak, right? It's Indian English that I speak. So I think you can easily understand that, right? Okay. So, and this channel is in English because we want to cater to all the audience out there who only understand their regional languages, right? So, the problem that they face is there is no good content maybe in the regional language, or maybe they're not able to understand chemistry or any other subject in the regional language, and also because the exam that they will be giving is in English, right? And they don't understand Hindi, right? So this is especially for those students, right, who are comfortable in English, right? So that language doesn't become a barrier in learning something, right? Okay, so now, as I told you, I have given you just one example. Different compounds will have different hybridization based on the coordination number as well, right? This we will see from the help of, with the help of some examples, right? How we are having this. This we have already seen. This I have already shown you, right? Now, how many hybridizations are possible, right? So if you have coordination number 4, then two things are possible. Either it can be sp3 or it can be dsp2. sp3 is a tetrahedral shape, right? sp3 is a tetrahedral shape. Now, any one of you, what is a tetrahedral shape? How does it look like? This is how tetrahedral compounds look like. Okay. This is how tetrahedral compounds look like. Can you see that? This is how, I'll just move this in 3D. This is how tetrahedral compounds will look like, and they have angle here which is same. If you put this here and put this here, it is the same compound. You put this here, it is the same compound. You rotate this, you are getting the same compound, right? That is your tetra. You can visualize it like this, you can see it like this, you can see it like this, you can see it like this, right? That is the compound that you have. Okay, let me just show you here as well, right? You can see it like this, like this, like this. This is the compound that you have. That is tetrahedral, right? It has an angle of 104 degree 28 minutes, right? That you can understand. And what is DSP2? That is a square planar geometry. That is a square planar geometry. Now, square planar means what? One atom, and at 180 degree opposite there will be another atom. This is the center metal atom. These white atoms here are representing the ligands. Okay. Then at 90 degree you will have another, and here also at 90 degree you will have one more. Doesn't it look like a square? 1, 2, 3, 4. It looks like a square, right? So that is a square planar geometry. Planar because it's in one plane. In one plane, right? It's in one plane, so it is called square planar, right? Thank you, beta. Thank you so much. Okay, understood? Beta, just give me a... I think for the first 30 minutes, my throat is okay. But after 30 minutes, it starts paining again. So, just give me a second. That's why I'm taking very small topics. This doctor has advised me not to teach for longer than 1 hour. So that's why I'm taking small topics. That's why I took one extra class today. That I can take extra lectures, but I don't want your syllabus to get paused. Okay. So now that is square planar, right? Okay. Now, who will tell me what is trigonal bipyramidal? Not even one question will be based on trigonal bipyramidal here. But still, no. If you want to know what is trigonal bipyramidal, I'll just give you one example of that. How does it look like? Right? So, trigonal means one triangle, okay? So, firstly, I'll make one triangle here. 1, 2, and the third one. Right? And the third one. I'm just making this here. This is trigonal. In chemical bonding, you also have Vesper theory VBT. There also we'll talk about these shapes in more detail. But there we will not talk about coordination compounds. Right? This is triangle. This is trigonal planar. Right? One center metal atom, 3 ligands. But here we are talking about trigonal bipyramidal. One pyramid above. Can you see this is forming a pyramid here, right? One phase here, one phase here, one phase here. It will form a pyramid here, right? Two pyramid means here also you will have a pyramid. right? So this pyramidal and this is also pyramidal. So it's triangle, trigonal, right? And two pyramids, trigonal, bipyramidal, right? Okay, trigonal, bipyramidal. Thank you, Rahul. So then we have coordination number 6, right? It can have two cases. Both are octahedral only. Let me just show you how does octahedral look like. It is same as square planar. It is same as square planar, right? All you have to do is put two more atoms in square planar. This is square planar, 90, 90, 90 degree, right? You put one at 90 degree, right? Below also, opposite to that, 90 degree. This is how a octahedral looks like, okay, in 3D. This is how it looks like. You see all the angles are at 90 degree. This with this, these two are 90 degree, these two are 90 degree, these two are also 90 degree, these two are 180 degree, right? So opposite are at 180 degrees, otherwise all of them are at 90 degree with each other, right? Okay, and our focus is going to be on coordination number 4 and coordination number 6. Firstly, we will see coordination number is 4 or 6. For 4, you will have two possibilities here, right? For 6, you will have two possibilities here, right? Here we are using inner d orbital, so it is also called inner octahedral. Here we are using outer d orbital, so it is also called as outer d orbital, right? Okay. Next postulate is based on under the influence of strong field, the electrons can be accommodated, forced to pair up against Hund's rule of maximum multiplicity. So Hund's rule says that you have 5 orbitals. You want to fill 7 electrons here. Firstly, singly filled all the electrons, right? But if you have a strong field ligand, that will cause the pairing. It will be 7 now. 1, 2, 3, 4, 5, 6, 7. This is for strong field ligand which cause pairing, which will cause the pairing. And the answer why some ligands are strong field, ma'am, why some are weak field. So weak field ligand will, this is weak field, no pairing. This is weak field, no pairing, no pairing. And here, another important thing is it will have no pairing. Moreover, after this also, moreover, what you will have here is there is no pairing here, but it is also called as inner octahedral, or you cannot say that it's inner octahedral. Yes, I think weak field ligand, yes. Hai? Yes. So it will be strong field ligand and this will be weak field ligand, right? Okay. Now let's talk about it. Here you can write one thing that I forgot. This follows Hund's law, rule, and strong field ligand is against Hund's rule. Against Hund's rule. Okay. If you see this here, I showed you this here, right? Now, can you see one thing here that here it was causing pairing. So it was against the Hund's rule, and rest of the orbitals, because it's a coordination number 6, that's why either it can be D2sp3 or it can be sp3d2. Only two possibilities are there. If it is causing pairing, we have D2sp3, and if it is not causing any pairing, like here you have weak field ligand, which is not causing any pairing, here you will have sp3d2, that is the outer octahedral complex. Okay. Now, one by one, we'll see some examples, right? Strong field causes pairing. Now, you will see, ma'am, what are strong field ligands? Examples. But in strong field ligand also there is one very good point SS, very good point SS. It, see, in one orbital you can't have 3 electrons. So forcefully this will be 1 electron that will be left here, right? In some cases, this 1 electron will jump to some other orbital. There are some examples like that. For example, it's a very good question that you have asked. So I'll just explain that, right? So if you see, if this would have been a strong field, if this would have been octahedral, coordination number 6, then this orbital, it would have shifted in cases this happens, okay? So here also I'm drawing the same thing. This is S, this is sp3. Now, if it's a coordination number 6, and here if it's a coordination number 4, okay? So let's see what we can do here. Let's see what we can do here for this 1 electron, right? Here electrons, this particular electron that will jump, and where it will jump, if I want to make coordination number 6, then it will jump 1, 2, 3, and this is not always, this happens sometimes, okay? So this can have D2sp3, right? Then if you talk about this one here, if it is coordination number 4, then I think it's already there. You will have, it's already there, 1, 2, 3, 4, 5, 6, 7. Then you will have sp3, no, dsp2. You will have dsp2. Okay, we have to make it like that. Okay, if the coordination number 4, in your mind it should be like either it can be sp3 or it can be dsp, right? And this is becoming dsp2 only. But if coordination number is 6, it can have sp3d2 or it can have d2sp3. Now sp3d2 if I make here, then one orbital will remain empty, right? So either this will remain empty, because these are the exceptional cases, okay? These are not usual cases, right? Either this can remain as it is and it will become sp3d2 and this will remain empty, or it can become d2sp3 by making this 1 electron jump to some other position. Okay, got it, right? Tell me, students, if that is clear or not. Okay, this is not usual case. I'll also explain you about the exceptional cases, right? Okay, now, right, let's talk about this. But it can move, let's say this is sp3d2, there is also 1d, it can move to this place, right? If we want to make like 1 extra electron. So this also happens. Or it will stay as it is only. It's not like 1 unpaired electron. I am not saying that strong field ligand will never have 1 unpaired electron. No, I am saying that it will try to pair all the electrons. Now, if you have 7 electrons, see, if you have 7 single person out there are 7 single people, right? Okay. So out of them, they are going on a vacation, or maybe some club they are going on where entry is only provided to a couple, right? So 2 can pair up. One will remain extra only, no? One will have to remain extra, right? So this thing will happen, right? So don't worry about the single electron. These are the possibilities that can happen depending upon various factors. Depending upon that, we will learn in CFSC also. Okay. Now, ma'am, whether this electron will jump or not, the reason will be in CFSC, crystal field theory. Okay. That reason we will learn in crystal field theory. First, you tell me if that is clear. right? Okay, students, shall I move ahead? Shall I move ahead? Right? Now, ma'am, how do we learn that these are strong field and these are weak field? That also we will learn in CFT, because the demerit of VBT theory. Achha, I'll tell you a very interesting point about VBT theory in the end. Okay, in the end, I'll tell you a very interesting point. You will be shocked to know that. Okay, the demerit of the limitation of VBT theory. See, CFT theory will explain which is strong field. It's a very important point that I'm telling you right now. Students don't know this. This is scram things. In reality, VBT theory never told us that this is strong field, this is weak field. This is what we know from CFT. You know what happened? What happened was VBT theory was given. See this. VBT, this will explain a lot of things that, the confusions that you are getting. VBT theory was given. In VBT theory, they used to see, firstly, they used to see which is paramagnetic and which is diamagnetic. Paramagnetic, or they used to see that which has more number of unpaired electrons, right? They used to see less unpaired electron, and here you will have more unpaired electron. Then they said that, okay, some ligands are causing pairing and some ligands are having no pairing. When we solve the questions, we do it in reverse, but the actual theory was opposite. What we do is we firstly see the oxidation number, then we see whether it's a strong field or a weak field ligand, then we cause the pairing, then we tell that whether it's para or diamagnetic, right? In the questions, we do reverse of what was the actual theory. Actual theory was that firstly scientists observed. That's why this is a limitation in VBT theory, that VBT theory was not able to predict magnetic behavior, right? Student asked that, ma'am, in VBT questions are asked on, tell me whether this is para or diamagnetic, what is the number of unpaired electron, what is the magnetic moment. Questions are asked like that. But why in the limitation it is that it does not give magnetic behavior? Because firstly, they understood the magnetic behavior by doing experiments, by experimental data, whether it's experimental data. They understood this with experimental data. Then they understood, okay, in CN it is showing pairing. So that means CN will be strong field. In Cl, in chlorine, bromine, iodine, it is never showing any pairing. That means that is weak field, right? That's how this theory in reality is. Now, that's why there are so many exceptions of this theory, right? Usually what happens, this is the general case, that NH3, EN, CN, CO, these are strong field ligands, very famous ligands, and these are the weak field ligands. Scientists observed that mostly in these cases, there was no pairing of electrons. But ma'am, are there any exceptions? Yes. There are exceptions that I have written here. As I told you, this theory was not formed that way. It's not like in this theory, the real theory will be CFT, where we will try to understand everything. But here, it's like forcefully he did this. I'll tell you. We are saying that H2O is a weak field ligand. Oxalate is a weak field ligand. H2O and oxalate does not cause pairing in general. You will see H2 always as it is not causing pairing. Oxalate means C2O42 negative. It is also not causing any pairing. Then, why here it is behaving as a strong ligand? We are saying with cobalt 3 positive, it is causing pairing. Another limitation of VBT theory. Firstly, he said that water is a weak field ligand, right? Then he was getting that in cobalt 3 positive, water and oxalate both are behaving as strong field ligand. So he forcefully made the pairing. He forcefully did the pairing. There was no logic behind VBT that why it is giving any pairing. Forcefully did the pairing, right? He then explained it that this water and oxalate, when it sees some metals in the higher oxidation state, it will cause the pairing. Forcefully he did the pairing, right? Now, water is a weak field ligand, but with copper 2 positive, it acts as strong field ligand. Water is a weak field ligand, but with copper 2 positive, cobalt 3 positive, it acts as a strong field ligand. Right? Nickel 4 positive, with nickel 4 positive, fluoride ion, halogen, it is supposed to be a very weak field ligand. But here, it is behaving as a strong field ligand with Ni4 positive. Very important, right? Then if you see cobalt 3 positive and Fe3 positive, NH3 also behaves as a strong field ligand. That is the general case only here because NH3 is a strong field ligand. We don't even need to write it here. NH3 usually behave as a strong field ligand only. But very important, like Fe2 positive you have, Mn2 positive you have, it is behaving as a weak field ligand with manganese and iron 2 positive. So in some 3D atoms, sorry, 3D metals, this when they are in the lower oxidation state, right? They are in the lower oxidation state. It behaves as a weak field ligand. So this is also a very important exception. These two are very important, very, very important, right? And this is also important. But first 2 points are most important. Then this point is also very important, guys. Mark this. Questions are asked based on this PT, PD and AU. If its coordination number is 4, you will do DSP2. PT, it exists as a square planar compound. So this is observed that PT, PD and AU, they would want to make a square planar geometry, right? Okay. Yes, Rahul, definitely. NEET aspirants and JEE aspirants have the same syllabus except for the JEE advanced syllabus, right? Okay. Now, let's understand this magnetic properties, right? That I told you that coordination compounds have partially filled d orbitals show characteristic magnetic properties. So depend upon oxidation state, electronic configuration and all of these things, right? And the ligand field, whether it's a strong field or it's weak field right? It depends upon that as well. Right, so based on that, you will have two things. One is diamagnetic, where all that means in diamagnetic, what you have? All the electrons are paired up, right? Wait a minute, yes. Paramagnetic is where you will have unpaired electrons. At least one unpaired electron will also work. And if all the electrons are paired, magnetic moment will be 0. But if you have at least one unpaired electron, magnetic moment will not be equals to 0, right? This will be equals to this simple simple formula here, under root n plus 2. And here you have a simple trick also. If unpaired electrons are coming out to be 1 or 2 or 3 or 4 or 5, see, more than 5 it cannot happen. After 5, 1, 2, 3, 4, 5, it will start pairing, right? So only these 5 possibilities are there. Either you can put this formula under root 1, 1 plus 2 is equals to under root 3, or you can just directly solve 1.7, 2.8, 3.8, 4.9, 5.9. That's it. 7, 8, 8, 9, 9. Okay, that will be your magnetic moment, mu. right? Okay, so that's a simple way, right? Now, let's understand firstly coordination number 6. Different examples we are going to do for this one, right? Now, you have coordination number 6. So when you see coordination number 6, one thing should click in your mind that either it can be sp3d2 or it can be d2sp. And this is how it looks like. Okay, this is how it looks like. These are 4 in one plane, these two and these two and these two, and here one is above the plane, one is below the plane. Okay, that's how it looks like in the 3D. Okay, now why it is called octahedral, that also have a very unique story that will understand it more in depth in isomerism. It has octa because it has 8 phases. First phase, second phase, third phase, fourth phase. Right? Similarly here, fifth phase, sixth phase, seventh phase, and this is the 8th phase. It has 8 phases. Right? That's why it is called octahedral. Right? Usually, like we are like, ma'am, it has 6 ligands. So why octa? Why 8? Because of 8 phases. Right? Now, in octahedral, 2 things are possible. Right? Either it can be outer or it can be inner octahedral. Let's see one by one with the help of examples. Cobalt F63 negative. Okay, so what I'll do now? What I'll like to do is, what I would like to do is, I would like to have it here, right? When I myself write now, then I know that you understand it much, much better. So I prefer writing only, right? Okay. Now, first thing that you will do here is, you will try to find out the oxidation state. Okay. So what is going to be the oxidation state that you have already seen, ma'am? Now, you know what? How VBT theory was made. VBT theory was made like this, that how VBT theory was made. In experimental data, they observed that this is paramagnetic, right? This was the experimental data. Now, firstly, they observed the oxidation number x minus 6 is equals to minus 3, so x is equals to plus. Cobalt is 4s to 3d7. Cobalt 3 positive will be 4s0, 4s0, 3d7, right? So here you will have d orbital, then you will have s orbital, right? Then you will have p orbital. You need to have octa. That means you can have one more d orbital here. So for that, what I'll do, 1, this is 2, and this is going to be 3. No, this is going to be 5. Okay. Now, what you will have here is, firstly, I am telling you how VBT theory was made. Okay. I am not telling you how you will solve it. I am telling you how it was made. Right. So, how it was made is, firstly, the scientists know that this is a paramagnetic compound. They know this. They don't know F negative is weak or strong. Till VBT, they had no idea about what is strong, what is weak field, right? They know that this is paramagnetic. Now they were like, okay, this is paramagnetic means forcefully. No, that means I can't pair it, because how it will have unpaired electron, right? So if it is paramagnetic, that means there will be no pairing, right? So here that's why this will be 7 electrons, 1, 2, 3, 4, 5, 6 and 7. In fact, it will not be 7, it will be 6, right? 6, right? So here we will write it 6, and here also you will have 6 electrons. Okay, here also you will have 6 electrons. So here it will be 3d6. 6 electrons. You can't cause the pairing because it is given in the data, right? That's how they predicted that this is going to be sp3d2. 1, 2, right? 3, 4, and this is going to be sp3d2. Now, you don't have the experimental data. So for you, they will ask you it in reverse. They will not give you its paramagnetic. They will just say this is the compound, this is the question, how they ask you the question. Okay? Because they don't expect you to remember experimental data, right? But they expect you to know that this is weak field or this is strong field, right? You have calculated this. This is a weak field ligand. So that's why no pairing. So now you solve it like this. Then you will say 1, 2, 3, 4, 5 and 6, and we are left with these 5 orbitals, right? And that these 6 orbitals. So that's why it will be D2sp. That's why it will be sp3d2. Okay. Yes, students, understood how VBT was made and how we solve it in today's world. We got to know about strong field, weak fielding from CFT. Crystal field theory will give us this. It will also give us proper spectrochemical series of like a data, like which are like in increasing order of field strength, right? Okay. Now that is done. And hence you can say that what is going to be the answer, right? Okay. Now, outer d orbital you are using, that's why it is called outer orbital, right? It is paramagnetic because it has an unpaired electrons. And how many unpaired electron it has? 1, 2, 3, 4. So mu will be equals to 4.9 Bohr magneton. Right? 4 unpaired means 4.9. Right? And here it is a high spin or spin free complex. What do you mean by that, ma'am? See, low spin complexes means number of unpaired electrons will be less. High spin means number of unpaired electron will be more. So when you have a weak field ligand, it causes no pairing, and that's why it causes high spin complex. High spin complex. But strong field ligand causes pairing, and that's why it corresponds to low spin complex. Right? Okay? Low spin complex. Okay? Yes, everybody? Now, let's talk about the next thing. I hate doing this. Sure. NH3 with cobalt. NH3 is a strong field ligand or a weak field ligand? Everybody. NH3 is a strong field ligand or it's a weak field ligand? What kind of ligand that is? Let's suppose nothing is given to you. Okay? Then how you will solve it? Now, if you see this here, cobalt, let's find out the oxidation state. X plus 0 is equals to plus 3. So X is equals to plus 3. Because this NH3 is neutral ligand. It has 0 charge. So cobalt is nothing but 4s2 3d7. And cobalt 3 positive is nothing but it is 3d6. Now here you have a strong field ligand. So what will happen? This is D, right? Then you have S, then you have P, right? And then you have again D, right? And here, if you draw the lines 1, 2, 3, 4, 1, 2, and 1, 2, 3, 4. Right? Here you have 7 electrons. So put the 6 electrons here you have. 1, 2, 3, 4, 5, and 6. Right? Now ligand is approaching. It's not like initially only it has pairing. Now the ligand is approaching, they are so scared, they are like, let's pair up. Some big gang is out there, right? So they will pair up, right? So they will pair up, right? Now here what will happen, right? When they are pairing up, 1, 2, 1, 2, 3, 1, 2, 3, 4, 5. When they are pairing up, then it will cause 1, 2, 3, 4, 5, 6. Now you have these D2sp3 that will actually make a hybridized orbital, right? Where you will have 1, 2, 3, 4, 5, and each of them will have donation from the ligand. That is, this is D2sp3. Here also this happened. Here also this happened. Here also they formed. Here also they formed hybridized orbital where electrons from the ligands were getting accommodated. Okay? Is that clear? Okay. Yes, everybody. Jack, right? You will be provided with one Telegram channel, right? So what you do is on the Telegram channel in the comment section, message me your ID, your phone number, so that I can ask the team to contact you. Okay? So basically that Telegram channel we have made for your queries only. Okay? So in the latest post, just write it down in the comment section of the Telegram channel. Right? Okay? Or tomorrow I have Sigma batch class. You can tell me in the class itself. Like 2:30 p.m. I have Sigma batch class. Right? So in the class itself, if you're not comfortable in that class itself, you can share your ID, everything, and I'll contact to the team. Okay? Right? Yes, HSEC, definitely you can join a club here, right? Because you still have time for your JEE Advanced, so that will be a very good choice, right? Okay, yes. I think now it will be an amazing point. In fact, I was thinking of starting JEE Advanced preparation also. In between lectures, it is going on, but I want to have a different problems like problem solving series for JEE Advanced questions. Okay. So do let me know in the comment section as well who are watching this on the recorded version. Do let me know in the comment section. Do you want me to take up like questions like at least once in a week, right? Only the questions of JEE Advanced from the chapters that we have already done, because till now we have done enough amount of chapters. From 12th we have done 5 chapters including this, right? So we can start with the JEE Advanced questions from now. Okay? Yes. Now, next is this we have done. So here it is. Is it low spin? Yes. Why? Because there is no unpaired electrons. Here magnetic moment is equals to 0. So that's why it is diamagnetic complex. Right? Okay. Spin paired complex. Right? That is spin free. Now you have coordination number 4. Right? Coordination number 4. Coordination number 4, you can have two things, sp3 or dsp2. Two kind of things will be there, sp3 or dsp2. Right? So when you talk about sp3 hybridization, that will give you tetrahedral complex like this. Like this. This is the tetrahedral complex and this is the square planar complex. So based on the hybridization, right, your answer will be changed. Either it can have this structure or it can have this structure, right? So one by one we'll see what will be the answer. If you see here sp3 is called outer complex, right, outer orbital. And here, because we are using n-1d in dsp2, it is called inner orbital complex. Right, everyone? Okay, everyone. Right. So here the question is NiCl. Now tell me, Cl is weak field or strong field? I told you. Cl is always a weak field ligand. It is always a weak field ligand. Okay. I feel like erasing the blackboard that I used to do in offline. Right? So now, if you see this thing here, sure, that's why it took me so much time. Okay. If you see this here, firstly, same pattern you will follow. What is the pattern? Firstly, what you'll have to do? Firstly, what you will see? You will see the coordination number. Coordination number is 4. That means either it can be sp2 or it can be sp3. Right? If coordination number is 4, either it can be, you can say, either it can be sp3 or it can be dsp2. Now, looking at the compound here, x minus 4 is equals to minus 2, x is equals to plus 2. Nickel is nothing but it is 28, so it is 4s2, 3d8. You take out 2 electrons here, it will become 3d8. Right? Cl is a weak field ligand. So tell me, students, will it cause pairing firstly? It will cause no pairing. This is S. This is P3. 1, 2, 3, 4 and 1, 2, 3. It will cause no pairing, so it will be, electrons will be filled this way. 1, 2, 3, 4, 5, 6, 7 and 8. Right? It is not causing any pairing, so we don't have this d orbital empty. So that's why it will be sp3. And this sp3 is going to make a hybridized orbital, that is sp3 hybridized orbital, where the electrons will be donated by the ligands, right? And hence this is going to be the answer here. Is that clear, everybody? Is that clear? Right? So here, can we see any unpaired electron? Yes. So it is, a number of unpaired electron is 2. So that's why it is paramagnetic. And here mu is equals to 2.8. Bohr magneton. Okay? Mu is equals to 2.8 Bohr magneton. Right? Is it a low spin complex? No, it's a paramagnetic complex. So it's a high spin complex. High spin complex. And this is weak field. This is weak field. That's how so many answers, they can ask you magnetic moment, they can ask you whether it's low spin or high spin, they can ask you number of unpaired electron, they can ask you hybridization, they can ask you the geometry. The geometry is going to be tetrahedral, right? These are the, it's a very important topic. At least one question, I would say 2 questions also they can ask you, but 1 you will definitely get from this topic, right? Okay. Yes. Now, let's see what we discussed here. It's a tetrahedral complex, right? That it's a tetrahedral complex that you will see like this, okay? And Outer NS and NP used in hybridization, the complex is called outer orbital complex, and it is high spin or spin free. High spin is also called spin free. Low spin is also called spin. Sorry, what was that? What was the word was spin paired. Okay, spin paired. It is spin free, high spin free, and that is spin paired. Rarely used, but yes. Right now. Okay, now tell me the answer for this. Cn, what is the oxidation number? Everything, right? What is the oxidation number? You've already seen that, I know that, right? So at least answer. You've already seen that, isn't it? So, what you will firstly say, 4 coordination number. So, either sp3 or dsp. It should click in your head, okay? So then you will say, what is the oxidation number? X minus 4 is equals to minus 2, x is equals to plus 2, right? Now when x is equals to plus 2, can I just directly write here that nickel, what it will do? It will be Ni, nickel is 28, so it is 4s2, 3d8. Nickel 2 positive will be 3d8. Now here you will have the pairing, right? In this case, you will have the pairing. So firstly, it will be D, vacant orbitals. This is S, P, and that we don't need to draw. Again, there will be D because of pairing will happen. I'm just drawing the boxes here, right? Okay. Now, 1, 2, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2. Okay. So now, what you have to fill here? 8 electrons. So firstly, it will be filled like this, right? 5, 6, 7, 8. Okay. Now, because Cn is a strong field ligand, it will cause pairing. Now, it will be paired up like this. 1, 2, 3, 4, 5, 6, 7, 8. Now, you will have this d orbital that is empty. So, it will form dsp2. Okay, it will form this hybrid orbital, that is this one, that is your dsp2 hybrid orbital, right, which will be having 4 rooms for 4 ligands to give the electron. So here it will be a square planar geometry with coordination number 4, right? It will be a square. What else they can ask you? Number of unpaired electron is 0, so mu will be equals to 0. So it's a diamagnetic compound. Okay? Understood, everybody? Tell me if there is any problem in this. Any problem in this, right? That we have solved already, and that's it, right? Okay. Now I'll do some questions on this, like proper your PYQs, what kind of questions are asked, everything, right? So, if you see this, it's a square planar geometry, right? We are using inner orbital complex, it's a low spin complex and spin paired complex. Every single answer we have here. Now you have JEE 2025 question based on VBT. Now it's a combination of chemical bonding and coordination chemistry, right? First two answers, these are not coordinate compounds. These are not coordination compounds, right? So I'll explain you the answer for PF5 and SF6 in chemical bonding. Oof. Now though it's raining a lot, guys. I think it's sometime I'll just end the class in next 10 minutes, okay? Tell me. This is the question. These two you don't have to find out. This will do in chemical bonding. Tell me about these two. Let's solve this. Let's solve this. Let me have an extra page here for this one. Okay. I think I should always get extra pages for you guys. Okay, so I'll just copy paste this here, right? And let's see what is the answer that we are getting. Oh, okay. Yes. Now, let's see that. One by one we'll solve. First is NiCO4. NiCO4. Firstly, we know that coordination number is 4. So either it can be sp3 or dsp2. Oxidation number is X plus 0 equals to 0. So oxidation number is 0 only. Nickel will be in 4s2 3d8. Right? And both of them electrons we consider. Okay? Don't just look at 3d8. These are also the electrons that will be paired up here. Okay? So here, right now what you have is, right now you have this 3d. Just write here. You have this 3d. This is S. This is P. Right? Right now what you have is this situation where electrons are being filled like this. 1, 2, 3, 4, 5, 6, 7, 8. Right? Then you have 4s. This is the thing that you have. Now, when strong field ligand, which is CO, which is a strong field ligand, this is a strong field ligand. It will cause the pairing. When this will cause the pairing, what will happen? It's a major mistake that, it's a silly mistake I would say that students do, right? So don't do that, right? Now, you will have to pair up these 2 electrons as well. It is going to pair all the 8 electrons and 2 electrons here equally. So it will be 1, 2, 3, 4, 5, 6, 7, 8. Now, do you see we have DsP2, DsP2, right? Okay, DsP2, right? So we can say that this is a square planar geometry. It is having no unpaired electrons, so n is equals to 0, mu is also equals to 0. And it is dimagnetic complex, right? So we can say it's a square planar, that means it will be DsP2, that means C will be 1. C is 1 in which of the following cases? DsP2. Wait a minute. Why there is no C1? DsP2, electrons 8, 9, 10. It will be paired up. CO0, nickel is 4s2 3d8. Let me see why it is so. Wait a minute, guys. Wait a minute. Wait a minute. Nickel 2 positive. It will cause the pairing, no? Acha, wait a minute. What I have done here? Wait a minute. Wait a minute. Oops. I'm so sorry. I'm so sorry. I'm so sorry. I am so sorry, guys. My bad. This was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. And that's what I was explaining you. Oh, silly mistake. Very silly mistake. I was teaching you, I did a, like myself, I did a silly mistake, right? So both the electrons will include. Now that's what I was teaching you. 8 plus 2, 10. So it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And it will be a sp3 hybridization. Let's see how your whole answer is like changed based on just one thing. And it's a tetrahedral species. Okay. So, yes, right. So that's why this will be sp3 and that is going to be 4, right? Now let's see PtCl4. See, I told you that if you remember this exception here, if you remember this, you don't even have to solve this. If you remember this exception here, like important point, not the exception, PT, PD, AU want to have DSP2 configuration, right? So automatically it will be paired up. It's a very interesting point here. Cl, Cl is it's a very important structure. PtCl4 2 negative. That's why I have written it in an exception. Okay, PtCl4. You don't even need to solve it. If you have read the exceptions, we already know PT, AU, PD, they all want to be in DSP2 configuration. Now, why it is under the exceptional cases? Because if you see this here, it is x minus 4 is equals to minus 2, so x is equals to plus 2, and here we have this is D, S, this is P, right? If you see this here, 1, 2, 3, 4, 1, 2, 3, 4, this is 1, 2, okay. Designing also should be good now. So it is existing in +2 oxidation state, right? Now, if you see PD here, it belongs to which compound? Which particular D should be there, right? If you see this here, right? PT, right? If you see this here, this is +2 oxidation state. We know that in +2 oxidation state, how it will be having? It will have 5D. This is going to be 6 and this is CX2. Yes. Okay. Now, what it is going to have, you don't have to see 5D or 6s, that you don't have to see. You just know that it is PT, and we know that in PT there is an exceptional case here, right? And here what will happen? The electrons of 5D plus 6s will pair up here. Reason, because PT, PD, AU, it doesn't matter they have a weak field ligand or a strong field ligand, even weak field ligand will cause pairing. Even the weak field ligand is going to cause. Hello. Am I audible? Am I audible? Yes, students. Hello. Yes, everybody. Voice problem you are saying, her Ram Charan. Yes, everybody. Am I visible? Am I audible? Yes, everybody. Am I visible? Am I audible or not? Then how you are able to hear that I am not audible? It's like, can you see me? Can you see me? No, ma'am, we can't see that you are wearing that Vedantu's black t-shirt and you're tying up your hair. Yes, ma'am, we can't see that you are like wearing the specs. Spammers, huh? Spammers. Okay. So, this is a very important point that you should know. right? Now, if you see PT, that is going to be 5D9 6S1, right? Now here, what you will have is, you take out 2 electrons, this will be 5D8, right? And here, when you cause the pairing, when you just don't cause the pairing, it will be 1, 2, 3, 4, 5, 6, 7, 8, right? But when you cause the pairing, now I have told you this here, that PT, PD and AU will cause pairing. It doesn't matter like what kind of uh, ligand they have, weak field, strong field, they will always cause pairing, right? So it will be 1, 2, 3, 4, 5, 6, 7, 8. And what you are left with? You are left with this DSP2. So that's why I told you, you don't even need to solve it. PT, PD and AU will always prefer DSP2 configuration, whatever is the ligand. See, even this is a weak field ligand, but causes pairing. This is an important exception, very important compound. Okay, right? Yes, everybody. So that is going to be this, and C is going to be the first answer for you, right? And about PF5 and SF6, no, I'll tell you that in chemical bonding. That's not a part of coordination chemistry, right? Okay. Again, JEE 2025 question based on the same thing. Here you have all the coordination compounds, right? So now here you will have some exceptions as well, right? This we have already solved, guys. This also we have already solved. So x will be equals to 0. Here x is equals to, okay. So one by one we can solve it. So what I'll do here is, what I should do. I don't like this page as such. Let me see if we have any, we don't have any extra page here, right? Chalo. Do you want me to write it? Or do you want to just see the answer? If you want me to solve it for you, I can do that. If you want to just see the answer, we can do that as well. Both options we have, right? Page is prepared. Now tell me, chalo, I'll also write on one page, I'll also write only two things, right? So first is I'll be doing NiCO. This we have already solved, so I'm not going to solve it now. Just fastly I can do that. X is equals to 0 here, and nickel will be nothing but it will be 4s2 3d8. This is a strong field ligand. This is a strong field ligand. So that's why it is going to cause the pairing. So if it is D here, right, this is S, this is P. So directly you can cause the pairing here. 8 plus 2, 10. So it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you are left with this, that is sp3, that is tetrahedral. Okay? That is tetrahedral, right? So I can say this, and there is no unpaired electron here. Mu is equals to 0. So yes, right? Tetrahedral, mu is equals to 0, right? So A is 3. A is 3, A is 3. These two options are already eliminated. If you're able to find B also, you are sorted. So NiCN4, 2 negative. I'll be giving some rest to my throat. Now, it's a strong field ligand, right? But here it is nickel 2 positive. It will be Ni 2 positive, nothing but it is 3d8. We'll say 3d8. And here you will draw D, then S, then P, right? Then 1, 2, 3, 4, 1, 2. And because it is pausing the pairing, so I'll be like 1, 2, 3, 4, 5, 6, 7, 8. and you will have dsp2 here. So answer will be dsp2, that is nothing but it is square planar, but here mu is equals to 0. Okay, mu is equals to 0 here as well. So dsp2, that is square planar, but mu is equals to 0. So B is 2. That means this is going to be the correct answer. But we will solve for third also, that is NiCl4. NiCl4 2 negative. Okay, so let's do it fast. Last one is going to be very interesting. NiCl4 2 negative, is it? Yes. And then there is MnBr4 2 negative. MnBr4 2 negative. Let's solve it, okay? Let's solve it. Yes. Beta, it will come, right? By the time you can watch the sessions here. Okay? Great. X minus 4 is equals to minus 2. X is equals to plus 2. Nickel 2 positive is nothing but it is 3d8. Right? Here it is. So let's solve for 1 firstly. Right? You have Cl. Chlorine is usually a weak field ligand, and here also there is no exception. So here it will behave in a usual way, right? So it will not cause any pairing. So 1, 2, 3, 4, 5, 6, 7, 8. Here you will have sp3. That means it is paramagnetic because it has unpaired electrons, so it is paramagnetic. Number of unpaired electrons are 2. Mu is equals to under root n plus 2. You can do this, or you can just directly write 2 plus 8 Bohr magneton. Right? Tetrahedral 2.8. Tetrahedral 2.8 is this one. So C is 1. You can see that here. D is the last one. We know that the answer is going to be tetrahedral 5.9, but still let's see that. Okay, let's see. We don't need to solve it, but here we will solve. X minus 4 is equals to minus 2. X is equals to plus 2. Manganese is 4s2 3d5. Karman, it is 25 is the atomic number. Manganese 2 positive will be 3d5 simply, right? So you can say it is going to be 3d and 5. 1 and 2. Now make the boxes D, then S, then P, right? So 1, 2, 3, 4. Ma'am, we are bored of this. It's more irritating thing to draw these boxes again and again, right? Okay, yes. Now 5 you have. This is a weak field ligand. So 1, 2, 3, 4, 5. And here you will be left with sp3, and that's the reason it's tetrahedral. Number of electrons, unpaired electrons are 5. That's why mu is equals to 5.9 Bohr magneton. Isn't it the case? Yes. Okay. Understood everyone? Right? I hope so. You are able to understand that. And you also got the answer correct. Right? I am not giving you really old questions. Latest questions I am giving you. Doable questions, not at all difficult one, right? You can't say these are difficult questions, okay? JEE 2025 question. The correct order of these complexes based on number of unpaired electrons. Everyone, number of unpaired electrons. Yes. Simple, yeah. Number of unpaired electron, not a big deal. See, one trick is The one which has strong field, they will have the least number of unpaired electrons. So they have put here unpaired, unpaired, unpaired. D will definitely not be the correct answer, right? D will definitely not be the correct answer. Let's solve it. Four things you have here. One by one we'll solve it. Let's solve this. X minus 4 is equals to minus 2. Nickel is in plus 2 oxidation state. Nickel is in 0 oxidation state. This is X minus 6 is equals to minus 3. Iron is in plus 3 oxidation state. Cobalt is also in plus 3 oxidation state. Just have to tell that. See, cobalt in plus 3 oxidation state, we know that cobalt is nothing but it is 4s2 3d7. In plus 3 oxidation state, it will be 3d6. Okay. If it is 3d6 and it has a weak field ligand, it will be 1, 2, 3, 4, 5. 5 boxes you will have. Now, I'm just drawing it by dash. These are the 5d orbitals, guys. If you want me to draw it like this, I can, but it will be more time consuming. Okay. It will have 6, 1, 2, 3, 4, 5, 6. Total 4 unpaired electron it has. What about Fe3 positive? Iron is nothing but 4s2 3d6. You take out 3 electrons, it will become 3d5. You don't have any strong field ligand, so it will not cause any pairing. So you will have 5 unpaired electrons. So definitely this is going to be more. So FeF6 is more as compared to this. So this is eliminated. This is definitely eliminated. Strong field will never have more unpaired electron, right? We have these two options. Let's see Ni. Nickel in 0 oxidation state is 4s2 3d8. Right? You have a strong field ligand here, so it will cause the pairing, and the pairing will go 1, 2, 3, 4. Pairing will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Number of unpaired electron is 0. This is coming out to be 0. What about this one? Ni2 positive. Take out 2 electrons, 4s, it will be 3d8. Whenever you're taking out the electron, take it from s orbital. Okay. One, it is also strong field ligand, right? 1, 2, 3, 4, 5, 6. Okay. 3, 4, 5, 6, 7, 8. So you have no unpaired electron, that is 0. So this is going to be the correct answer, where these are equal. So answer is going to be C. Okay. Right. Correct, everybody. I think that was the last question, right? Yes. Now we will talk about, that was the last question, guys. Now we will talk about some limitations that I have already told you. Okay. Let's see. First is, it involves a number of assumptions, right? It is saying that forcefully you will pair, because he didn't tell us that, we made the exceptions ourselves. According to VBT theory, there is no theory that why this is a strong field, why this is a weak field. Forcefully pair them, forcefully don't pair them. It was going on like that. It does not give any quantitative interpretation of magnetic data. That means we will not be able to calculate magnetic moment based on VBT, right? You will say, ma'am, but we are calculating magnetic moment. VBT theory was different. VBT theory was, firstly, they will tell that this is para or this is di. then you will see where it is causing pairing, where it is no pairing. In reality, we are doing the opposite, right? So we are not following VBT theory. VBT theory was this is the experimental data, whether it's para or it's di. According to that, tell us which will cause pairing, which will not cause pairing. So he was forcefully pairing up some electrons, forcefully not pairing up some electrons, right? So that's why magnetic data was not available to us, right? That means magnetic data, he didn't tell us to like how to calculate. Okay, it does not explain the color. No talk about color. And color, they are asking questions based on that. So CFT theory we are going to do in next lecture. Very important theory. It does not give quantitative interpretation of thermodynamic or kinetic stabilities. This here not talked about. Does not make exact predictions regarding tetrahedral and square planar. I told you some exceptions. PT, can you see this is one of the exception only. Like I am telling you forcefully it is making this. If you see this here, Cl is supposed to be weak field. Still we are pairing this. So what's the logic behind that? Right? Forcefully we are just pairing it. So it is under exception only. That means if theory has lot of exceptions, that means there is something not good with that theory. Okay? Then it does not distinguish between weak and strong field. This distinguished thing was given by CFT, not VBT. CFT will tell us spectrochemical series. We are taking applications from CFT and then applying to VBT. That's how we are able to calculate magnetic data. But at that time, there was no talk about strong field, weak field, right? He didn't tell us about that, right? And that's it, right? Now, this is your question, guys. You can see this here. And I'll see how many of you are able to answer. Again, I am saying my throat is not at all good, in a good condition. Now it's paining literally, it's swollen from here, right? It's paining. I have fever daily. In the morning, I have fever, right? I'm on antibiotics and still I am here to teach you, right? If I don't see you guys doing homework, beta, I can easily take medical leave. I can easily take that. I'm not taking that because of you guys, right? So if you don't respond in the comment section, nothing, then I'll feel that okay, these guys are not interested, and I'll like take rest, right? So I'll see if you're able to answer that in the comment section or not. Totally your choice, right? Okay. So take the screenshot of this one and answer me in the comment section about this, right? And this is the second question that you need to answer me in the comment section, right? Lazy people, wake up and answer something, okay? So, students, today is 17th, right? And I would love to inform you this thing that the sale is extended till 19th, okay? And beyond that, it will not be extended, right? This is just for some lazy students out there who didn't see YouTube for like 3-4 days. So that's why we are extending this sale, right? You still have time where all the courses, like most of the courses are at 79% off. And I'll just show you that as well. If you see this here, right, in the comment section, right? When you see this now, it definitely breaks my heart to see you guys like, what to do. So, if you see this here, this is Sigma Express batch, right? Where the students are there in the batch itself. They are learning a lot of things, right? In the Sigma batch, and we have our daily classes there, right? Which is right now at just 1499, right? So the price has really decreased from this amount to this amount. And this is not going to be available for a very long time, right? Okay. So enroll yourself into the Sigma batch in this offer itself so that you can save some money as well, right? Okay. Sure. Okay then students, bye bye. Take care. See you all in the next class. Bye bye. And I'm waiting for your answers in the comment section. section. Bye bye.